All right, let's move on to speak about lipids. So lipids are composed primarily of hydrogen and carbon. So there isn't a whole lot of oxygen on lipids. And that's really going to help us dictate the difference in function with lipids. And this is something that we'll see again throughout the course. You'll hear me say this time and time again. Form follows function. The way something looks heavily dictates some functional component, some functional property. And we see this not only on an organismal level, right? The way fingers look, the way eyes look, the toes look, but we see this even on a small cellular and subcellular level, right? The way that an atom looks, the way that a molecule looks, dictates something about its function. So in lipids, we don't see a whole lot of oxygen, and we know oxygen is pretty much an electron hog, right? It's going to want to grab electrons, and so there's going to be an uneven distribution of charge around oxygen. And because we don't have lots of oxygen in lipids, we know that lipids are non-polar, so they're very equally charged around the molecule. And so this makes them hydrophobic. What does hydrophobic mean? It doesn't like water, right? They're non-polar because water is also polar. Water has oxygen on it, right? And so lipids and water do not play nicely together. They're non-polar, they're hydrophobic, and that's because of their structural makeup. There are 5 classes of lipids we'll talk about: triglycerides, ketones, phospholipids, eicosanoids, and steroids. We'll talk a little bit about the different structural properties and some of their functions. So triglycerides are our main and probably the simplest form of lipids in the body. They're our main source of fat. This is how we store fat and mobilize and use fat in our body. It's made out of glycerol backbone, which is a 3-carbon alcohol on this end here, and then 3 fatty acid tails that are attached on this end. Okay, there are different types of triglycerides, and once again, the way that the triglyceride is structured dictates something unique about its function. And you can have large functional differences that come about from very small structural changes. So for example, we have saturated versus unsaturated fatty acids. A saturated fatty acid, does anyone know what's the difference between a saturated and an unsaturated fatty acid? What's the structural difference? Yep, so the presence or absence of double bonds. Perfect. So if it has double bonds, it is unsaturated, right? It's not bound to its maximum capacity, right? But if it doesn't have any double bonds, every single carbon has hydrogens bound to it, and so we say it's saturated if it has no double bonds. Okay. An unsaturated fatty acid can also have 2 types. They can be trans or cis, depending on what face those hydrogens are on. So what face of the double bond do we find those hydrogens? If they're on the same side, we call them a cis fatty acid, and if they're on the opposite side, we call them a trans fatty acid. Now we can see these very minute differences in structure can dictate to us the difference between a good fat and a bad fat, right? Trans fats are much more unhealthy for our body and our vasculature than our cis fats. Likewise, unsaturated fats are much more unhealthy than saturated. Moving on, ketones. Ketones are an important sort of backup source of fuel. We see them if someone is diabetic or if they're on an intentional low carbohydrate diet. And basically, if there isn't a whole lot of carbohydrates around, the body can take some of its triglycerides, which is in the fat tissue, and it can release those and make send them to the liver and convert them into ketones. Now, ketones typically lead to a state called ketosis if they build up in the blood. And this is a sometimes life-threatening situation for ketoacidosis because they're quite acidic. They can change the pH of our blood, and this will lead us to an acidotic state, which can be fatal. So this is something we often look out for in diabetics or in persons who are on a severely low carbohydrate diet. They often give the breath this acetone taste or smell as well, this metallic kind of odor because of the buildup of the ketones in the blood. So ketones are typically, again, mobilized if there is an absence of glucose. We really want to point out here, glucose is the main source of fuel, the main source of energy. But in the absence of glucose, or if you are diabetic, which in that case you have difficulty with insulin sensitivity, or you are not producing insulin, and you need insulin to use glucose. So even if you have glucose as a diabetic, you cannot use it as efficiently, and so you must tap into another energy reserve, and you do so via triglycerides, which break down to form ketone. Okay? Now the structure of a ketone is a carbon double bound to an oxygen, with the R's representing two functional groups, which can be any combination of functional groups, and this gives us many different ketones. One of the more common ones being acetoacetic acid, which is represented here, that has a hydroxyl and a methyl group attached. So we can have different functional groups, which gives us different types of ketones. So you'll definitely see more than one type of ketone. All right, moving on to phospholipids. This is probably the most important lipids that we will come across. We're going to speak about them again and again, and we're going to speak about how they lend themselves to a very important structure of the cell membrane. So phospholipids are amphipathic. Does anyone know what amphipathic means? Both polar and non-polar. So there's one region of this very same molecule that is polar, meaning that it likes water, it's hydrophilic, and then there's another part of the molecule, which are the tails, that are non-polar, meaning that they are hydrophobic and they do not like to interact with water. Okay? This makeup, this structural orientation of phospholipids makes them very important in terms of mobilizing fats in our body, in terms of maintaining the structure of certain organs like the lungs, which I'll talk about. And so we can utilize this unique relationship of a phospholipid in many different ways in the body. So once again, we have that hydrophilic head and the hydrophobic tail. So this part of the molecule likes water, and this part of the molecule does not. Now, we mentioned that fats are non-polar, they're hydrophobic, but we need fats in our body, right? We need fats for our cell membrane, we need them for other parts of our body, we need them for hormones. So we have to have fats in our body. But we also know that the body is mostly made up of what? We talked about this last class. The body's made up mostly of water, right? Lots and lots of water. So if we need fats in our body and we also are made of lots of water, we've talked about those water compartments, the extracellular fluid, the intracellular fluid, how do we then get our fats to mobilize and move around in this aqueous environment? This is where phospholipids come into play, right? We have phospholipids lining our cells. They form the phospholipid bilayer, where those hydrophobic tails kind of face each other, and the hydrophilic heads stick out and face the aqueous environment. And this is how we actually compartmentalize our body. So this makes up our cell membrane, and this is what differentiates extracellular from intracellular. So they're very important molecules in compartmentalizing the water in our body. Likewise, the micelle, which is in the image on the right, is an important structure that helps us to move fats around. So because, again, the tails like fats and the heads like water, if we combine this ball of phospholipids, we could put our triglycerides in the middle of that micelle, and we can move our fats around in this micelle. Okay. At the bottom here, there's surfactant, which is another example of a phospholipid. And this is a substance that is secreted by the cells of the lungs, and they help to maintain that, maintain the patency of the alveoli and prevent them from collapsing on themselves. Surfactant is usually given to premature newborns, because if they don't have that lung developed well enough, they don't secrete enough of this on their own. And the ability of a neonate or newborn to breathe on its own is a really important part of whether or not they'll survive. So we usually give surfactant to newborns to help them keep their lungs open until the lungs mature enough. All right, eicosanoids. So our next class of lipids are eicosanoids, and these are basically modified fatty acids. So we take a large polyunsaturated fatty acid, like arachidonic acid, which is a lot of fatty acids attached to each other, a long chain, and it basically folds on itself in the presence of certain enzymes, and we create these molecules called eicosanoids. Examples of these are prostaglandins, thromboxanes, and basically they can be attached to certain cells and they can send certain messages or signals, right? They're signaling molecules or communication molecules. They can send messages about the immune system, which prostaglandins often do. They can send messages about certain states of the cells. They can talk to our other immune cells, like our leukocytes and lymphocytes. And so they're basically important in signaling and communication. All right, and then steroids, which are our last class of lipids. These are the more complex ring-like structure. These are derived from cholesterol, which is really abundant in our body as well. This is another reason that we need fats to make structures like this. They are found in a lot of our hormones: estrogen, aldosterone, testosterone, cortisol, our stress hormone. Thyroid hormone is also a steroid. So really important function of our hormones, and really important function of why we need fats in the body. Okay?